So as we're already over time, let's go straight on to Graeme. And after Graeme's talk, we have a break, and we can ask all the speakers more questions. So thanks a lot, Charlene. Graeme, you want to put up your...
Yep. And can you hear me all right?
Yep.
Okay. My internet's been unstable, so let's see if we can get through this. So hi, everyone. Thank you to the organizers. Today, I'm speaking about the supercooled Stefan problem and some processes with laws converging to it. So the supercooled Stefan problem, what is it? So we're looking at U, which is the temperature below equilibrium of some supercooled liquid. And this liquid is in contact with a solid. Initially, the solid is on the negative reals and the liquid on the positives. And then the boundary between the two regions increases. And so the evolution of the boundary is governed by this equation here. And this is the Stefan condition. So it says that the rate of change of the boundary is proportional to the rate of change of this negative temperature at the boundary. And so our liquid obeys the heat equation in this region gamma. So positive times and X is greater than the boundary. And we also have this equilibrium condition that says that the liquid takes equilibrium temperature, so 0 for water at the boundary. So this is an old problem. And one of the difficulties with classical solutions is that we can have finite time blow up depending on our initial conditions. And so recently there's been probabilistic reformulations that give us a sense of global solution in the presence of blowups. And that's what we're interested in today. So we'll go into that. What we do is we encode our initial temperature distribution in a density for a random variable x naught. And we take a Brownian motion B independent of that x naught. Okay. And then we're looking for a non-decreasing right continuous function lambda. This will be our free boundary that solves this problem too. So what is this problem? We have a Brownian motion with drift, xt, this stopping time tau, which is the first time that t hits 0. And then we ask that lambda is proportional to this probability that tau is less than or equal to t. So how does this connect to our original problem 1? If we look at this process, xt into k or tau greater than or equal to t, and its distributions, then we do this change of variable. So the x takes place on spatially on 0 to infinity. And so we're going to put in this shift spatially to go from our p's to u's, which will be a solution of the original problem. And so this is a weak solution. And these functions, they're non-decreasing, the right continuous, but they might have jumps and they might have points that are 1/2 Holder. And so the existence comes from probability theory using McKean-Vlasov limit. And then we also know things about the regularity. And there's also a particular physical condition that we can impose that will give us uniqueness as well. For today, what we're going to look at is connecting up these boundaries lambda from this probabilistic formulation to boundaries lambda epsilon, which come from a regularized PDE. And so these solve a classical PDE. So let's talk about that regularized problem. So here we have a little subscript epsilon for U epsilon. And we have two things that are different here. So the first, we can see our Stefan condition. Instead of an alpha, we have this alpha minus 2u epsilon in front of our lambda prime. And so we'll talk about that on the next slide. And then the other difference is that instead of having the liquid being at equilibrium temperature at the boundary, we want u epsilon at the boundary to be epsilon times lambda prime. So we can think about this in two ways. If lambda prime stays small, then as epsilon goes to 0, this will give us back our equilibrium condition. Another way to look at this, if we divide this thing through by epsilon, then for any fixed epsilon using the maximum principle, we'll have that u epsilon is bounded by its maximum initial condition. And so lambda prime will be no greater than the maximum of u epsilon divided by epsilon. So this is where the regularization comes from that prevents blowup. And then we have just the usual with a smoothing kernel for our initial condition. Okay, so now here's that Stefan condition that I told you about earlier. And so instead of just alpha, we now have an alpha minus 2 u epsilon. And so I'll talk about that. So first we tried this project just with alpha and things didn't quite work out. And so we dug into the applied chemistry literature, and we actually saw that what you can do is linearize this latent heat function. So when the temperature is constant, it will always be alpha. But if we let our temperature at the boundary deviate from the equilibrium, then we're just using a linearization here. And this makes things work very beautifully, as we'll see later. One of the things that happens, though, is we need this guy to be positive because we want our boundary to be freezing monotonically. We don't want things to go backwards. And also we need to prevent a divide by 0 sort of situation. And so we introduce this assumption on the initial data. This will propagate for all times by the maximum principle. And one of the things we get out of this for the probabilistic reformulation with these lambdas that might have jumps, if we have this assumption on the initial data, it actually renders those lambdas continuous, and there will only be a single solution to that problem. So it is unique, and that solution is continuous. Okay, so let's solve this regularized PDE. What we do, we look at this auxiliary problem 4. And so here we've conjectured some boundary lambda epsilon, and we have only one condition at the boundary for all times, okay? So we can solve this problem. It's no longer a free boundary problem, just using the classical linear parabolic tools. And then we define this operator here, f epsilon, that takes our input lambda epsilon and gives us back this time integral of the solution to 4. And so what we can do, if we have a fixed point of f epsilon, we can take a derivative of both sides of this, and we'll get back a solution to our regularized PDE. And so this is sort of a classic trick to get another boundary condition satisfied. And so the P's, again, we saw going between the probabilistic formulation and the solution to the original problem U. P is just when we shift the spatial domain from U. So that's why we see that our problem takes place on 0t times the positive reals. And so then we can go back by shifting again to solve our regularized PDE. Okay, so now we get to the processes part in the title of the talk. And so for this regularized problem, we have an associated process view of things. So now we have x epsilon is again a Brownian motion with drift lambda epsilon. We're doing something a little bit different though. We're going to reflect at 0 instead of absorbing. That's our Skorohod map psi here. And we're going to look at the local time process for this x epsilon. And so this is our main tool. If we look at these p epsilon tildes, which are densities of these sub probability measures u epsilon, then we have that the p epsilon tildes are equal to the solution p epsilon to our problem 4 almost everywhere. And the really nice equation that we get out of this, this is sort of the most beautiful part of this project, is that f epsilon of a given lambda can be expressed as this functional of the local time. And so this is beautiful. It not only holds for the limiting regularized boundary lambda, but we can put any lambda into it. And so this operator with, we want to have a unique fixed point. So we show it's a contraction, and then we can actually get our lambda by iterating. We can just put in lambda 0 is equal to 0 and run this thing. And in the limit, we'll get back our final lambda. Okay, so here's the results. For any epsilon, we can solve our problem. Again, this is a fixed point problem. And then we actually have that these lambda epsilon, this family increases pointwise as epsilon decreases. So it has a limit, and the limit agrees with this unique continuous global solution from that problem 2. And under our assumption that limit is continuous, and so we get this convergence uniformly on compact sets. And so we have time for just a little idea of the proof. So there's a monotonicity principle for the local times that gets upgraded to give us monotonicity for the lambdas as epsilon decreases. So we can take a limit in epsilon, and then we make our conjectured limit lambda tilde right continuous. And then we look at this process, which is a Brownian motion with drift lambda tilde and the stopping time tau. And so using our really nice Feynman-Katz formula, we write lambda as the following and split things up when tau is greater than t and tau is less than t. And so one of the things we have is if x hasn't hit 0 yet, then we won't have picked up any local time. And so we get just 1 here, e to the 0. And so this term here we see is thus the probability from this problem for the limits, the supercooled Stefan problem. And then this remainder term, we just have to show that it goes to 0. Any questions? Okay, I think I'm right on time. So thank you.
Thanks, Graeme. Well, I guess we have clap for everybody. We have a 20 minutes break, but I'm sure the speakers will be happy to answer more questions if anybody has them during the break. So thanks again to all 3 speakers. See you in 20 minutes.
And just one quick announcement. So Skander is not going to be able to give his talk today. So we're going to shift Fan to the 4 o'clock slot. So there'll be 2 talks in the remainder, Yevgeny and Fan.